Okay, we begin where we left off with section 1110, which is about X-ray crystallography, which is an interesting technique which is used to basically discern the pattern of arrangement in crystalline solids. And it has to do with passing X-rays through the different regular arrangement of the atoms in a crystalline solid, and the way that the X-rays bounce back to the detector can be used to determine how the atoms are arranged relative to each other. Going into any more detail than that, I think, is really beyond the scope of a normal general chemistry class. And I don't know why the text includes an entire section on this method, unless maybe Naval Tro spent years in graduate school working on X-ray crystallography, and he's determined to talk about it one way or another. That's my guess, anyway. It's kind of the way that I talk about mass spectrometry whenever I get a chance. But anyway, we're going to skip that section and go on to unit cells. Much of the information we have on unit cells was derived from X-ray crystallography, but really the knowledge of the unit cells themselves are the important thing here. Unit cells are ways of sort of looking at the overall arrangement of crystalline solids. And it turns out there are several different ways that you can arrange atoms relative to one another in a three-dimensional space that are different from each other, but still allow the atoms to get fairly close to each other, which minimizes the empty space. And that's generally the way that crystalline solids like to be. They like to have the atoms close to each other with minimal empty space. But like I said, there are several different ways to do that. And a unit cell is basically the smallest unit of the crystal lattice that gives you all of the information that you would need to reproduce the entire overall structure. So the different ways of arranging atoms in three dimensions would be known as different crystal lattices. And the particles are arranged in ways that minimize the potential energy. But there are several different ways that you can do that, and part of it depends on things like, excuse me, the size of the atoms, for instance, and what types of atoms they are, and the types of repulsions and attractions that they might experience for each other. And also the fact that crystalline solids are not necessarily made up entirely of atoms. We have some crystalline solids like sodium chloride that are made up of ions, and those ions can have attractions or repulsions for each other because of their electrical charges. We have some crystalline solids that are made up of molecules, where there are actually three-dimensional arrangement of molecules in 3D space. And those molecules could be polar, they could be nonpolar, and they will have certain attractions or repulsions for each other based on that, and also based on their size and shape. And so there's a variety of different crystalline lattices that we're going to be looking at. And the unit cell specifically is what you get when you cut the crystalline lattice down to the minimal size that's necessary for you to be able to reproduce the entire crystalline lattice. The analogy is often used between, say, a tile floor and one single tile. One single tile would be the unit cell for the tile floor, and the entire floor would be the crystal lattice. And assuming that it's the type of tile floor where all the tiles are the same, then all you would have to do to recreate the entire floor is take copies of that one tile and put them next to each other. In the case of a floor, it would be in 2 dimensions instead of 3 dimensions. And when you're done, you get the entire tile floor back. But the only information you really needed to do that was the information that's present in that one tile. because all the other tiles are the same and they just line up right next to each other. And that's kind of like the idea of what a unit cell is, only unit cells are three-dimensional. So a unit cell is the smallest portion of an overall crystal lattice that contains all the info needed to reproduce the whole lattice. Okay, so if you just repeat the unit cell over and over again, in 3 dimensions, that'll reproduce the entire crystal structure. Okay, so let's see, there's a figure on page 491 that shows a 2-dimensional unit cell. And if I can find what I did with the book here, we'll have a look at it. Okay, 491 has this diagram. Okay, and this is kind of analogous to the example of the floor tile, where you have an arrangement of circles in this case, because this is only 2-dimensional. And you'll notice that there's a repeating pattern of these circles. And if you map off a certain portion of this pattern, then you've got all the information you need to recreate the entire pattern just by repeating that one section over and over and over again. And in this case, the darker red square is basically contains everything you need to reproduce the entire pattern. Notice that sometimes, in fact, in just about all cases, the unit cell will, at least at the outside edges or the corners, will often not contain entire atoms. It'll only contain a fraction of an atom. And in this case, each corner of this unit cell only contains a quarter of each circle, because the unit cell next door contains another quarter of the circle, and the unit cell above it will contain another quarter of that circle, and the unit cell above the one next door has the fourth quarter of that circle. So the circles at the corners are actually divided up among 4 unit cells in this 2-dimensional structure. Well, you notice if you take this square, which is your unit cell, and put another one just like it next door, you get an extension of the pattern. And if you do that again, you get another extension of the pattern. And if you do one below it, you get another extension of the pattern. And eventually you get the entire pattern if you keep reproducing these unit cells by putting new unit cells right up against the edge of the ones that already exist. And what you see down below there, this is the beginning of 3-dimensional unit cells, which we're not quite to yet. Okay, so that's an example of a 2-dimensional unit cell. The positions where something resides, like if it's a unit, if it's a crystal lattice that's made up of atoms, then the places where the atoms are, or if it's made up of ions, this would be the places where the ions are, or molecules if it's a molecular crystalline solid. These are known as lattice points. It's basically where the stuff is actually located. And the lattice points usually fall at the center of an atom in most cases. And that's because most atoms or ions or molecules, whatever is present at the lattice points, most of the time, each of those will be divided up among more than one unit cell. And there's really only one exception of the common types of unit cells that we're going to be looking at, where you'll have an atom that's entirely within the unit cell and not shared with any other unit cells. But for the most part, you're going to be sharing each atom or each ion or each molecule with at least 2 unit cells. The unit cells are classified by symmetry. And most of what we're going to spend our time looking at will be cubic unit cells. Cubic unit cells are unit cells that are in the shape of a cube, hence the name cubic. And that means they have equal length edges. Their sides have the same surface area and angles of 90 degrees. And these are the simplest of the various types of unit cells. Some unit cells can get extremely complicated. Fortunately, we're not going to go that far into it. We're going to take a look at the cubic unit cells and a couple of the more common ones beyond that, and that'll pretty much be it. So under cubic unit cells, you've got simple cubic, which, as the name implies, is the simplest of the cubic unit cells. And it features an atom that is centered at each corner of the cube. And what that means is each atom is shared by 8 unit cells. Or in other words, 1/8 of each atom is within any given unit cell. So, it's easier to imagine when you look at the diagram, which is also on page 491. And that is the purple thing that was right under the picture that we just looked at. Notice the way that this is divided up. All you're seeing will be in this particular representation, all you're seeing are the portions of the atoms that are within this one unit cell. But if you look at the shapes, yeah, this is clearly a piece of a sphere. And in fact, each of these corners is 1/8 of a sphere. And so this sphere that's centered at this corner right here that I'm pointing to, 1/8 of that sphere is in this unit cell, but another 1/8 of that sphere is in the unit cell next door, and another 1/8 is in the unit cell in front of this unit cell, and another 1/8 is in the unit cell in front of the unit cell next door. So that's 4/8 accounted for. That's half of the atom. Plus you do the same thing again in the next layer up. So the unit cell right above this one has another eighth of that atom. The unit cell next door to that has another eighth, and the unit cell above and in front of this unit cell has another eighth, and the unit cell next door to that has another eighth, and that is all 8/8ths of that atom, because that one atom, like I said, is shared among 8 different unit cells, 4 in this layer and 4 in the layer right above. And the same is true for each of these other atoms at the corners. Another thing you might notice about simple cubic unit cell is that the edge length is equal to 2 times the radius of the atoms, because the atoms are considered to be touching within this simple cubic unit cell. And so if the atoms are touching at the center of each edge, that would mean that from a corner halfway to the other corner, or to the next corner, that would be 1 radius of a sphere, because you're going from the center sphere to the outer edge of the sphere. And then going the rest of the way to the next corner, that would be another radius, because you're going from the outer edge of the next sphere to the center of that sphere. So that's 2r. So the edge length is 2r. Or in other words, the edge length is equal to the diameter of one of the spheres that makes up the simple cubic unit cell. Okay, so the edge length is 2r, and 2r being the radius of a sphere or an atom or ion or molecule, if that's what you're talking about. And this is assuming that the atoms touch, which we do usually do make that assumption. The volume of the unit cell is just edge length to the 3rd power, because that's the volume of the cube. It's L to the 3rd power. L in this case is 2r. So 2r to the 3rd power would be the volume of the unit cell. Or in other words, 8r to the 3rd power. So now if you know what the radius of the atoms that make up the unit cell are, then you know what the volume of the unit cell is. It's just 8r to the 3rd. There are many cases in which it is desirable to know how many atoms are within a unit cell. Because one goal of crystalline packing, basically one goal of forming crystalline solids is to get the atoms to be as close to each other as possible, or in other words, to have as little empty space within the unit cell as possible. And that tends to minimize the potential energy and make the structure more stable. And one way that you can tell how close the atoms are, or how much empty space there is by adding up the total number of atoms within the unit cell. The more atoms there are, the less empty space there is. So more atoms within the unit cell would mean more efficient packing, and that generally means lower potential energy, which means stability. And nature generally favors greater stability. For a simple cubic unit cell, as we mentioned, as we saw when we looked at the unit cell, what's inside the unit cell is actually several pieces of atoms. For the simple cubic unit cell, there is no single atom that's completely within the unit cell. So what we have to do is basically add up all the fractions of atoms that are within the unit cell. So we have 1/8 of an atom per corner of the unit cell. So remember this structure here, 1/8 of an atom per corner, and a cube has 8 corners. 1, 2, 3, 4, 5, 6, 7, and then the one in the back, 8. So 1/8 of an atom per corner times 8 corners means that there's a total of 1 atom within a simple cubic unit cell. And this goes for all of the simple cubic unit cells. The one that I showed in the book was, they didn't even name what atoms those were that were in that arrangement, because it doesn't matter. It doesn't matter, whether it's a metal or a non-metal, or whether it's a large atom or a small atom. You still, if it's simple cubic, you still get 1 atom at each corner. 1/8 of an atom is inside any given unit cell, and a cubic unit cell will have 8 corners. So it's 1/8 times 8 for 1 total atom within the unit cell. There's also a concept known as the coordination number. And the coordination number is just the number of atoms that any given atom is in direct contact with. Okay, and for simple cubic, you could look here and see, okay, we'll choose this atom here. It's in direct contact with this atom and this one, plus 2 more in the same layer, plus the same number up above. Or sorry, 3. So it's in, right. This one, and this one, plus the same above. Sorry. So it's 6. So the coordination number for a simple cubic unit cell will be 6. And again, it doesn't matter what element is making it up. And here are some more representations of ways to look at simple cubic unit cell that you can see. So this is showing the entire spheres. And this just shows what's within the 1 unit cell. And up at the top of the page, there is a table that gives these criteria, like what is the coordination number, number of atoms within a unit cell, what is the coordination number, what is the edge length equal to in terms of the atomic radius, and also the percent packing efficiency for the various types of unit cells, because some of them are more efficient than others. All right, so so 6 is the coordination number for simple cubic unit cells. There's a related concept known as packing efficiency. And packing efficiency is just the percentage, sorry, of the volume of the unit cell that's occupied by spheres or atoms, if you're looking at it that way. Okay, so to calculate the packing efficiency of a cubic unit cell, well, if it's the percent of the total volume of the unit cell that's occupied by spheres, there are a couple things you need. You need the volume of the spheres within the unit cell, and you need the total volume of the unit cell. Okay, the packing efficiency will just be the volume of the atoms, or spheres or ions or whatever the substance is made up of, over the volume of the cell, times 100. And for a simple cubic, it's 52%, which is, not all that good, really. You can actually work it, to see how you can work it out. One way you can work it out is if you know what the actual radius of the atoms is. You can work it out that way. But actually, even if you don't know what the radius of the atoms is, you can just leave the letter R in there, and it ends up canceling out pretty quickly in the process. So the volume of the atoms will be, well, the volume of a sphere, is 4/3 pi r cubed. And there's one atom total within the unit cell. And so that's 4/3 pi r cubed. The volume of the unit cell, well, it's a cube. So it's just edge length to the third power. Edge length is 2r. So 2r, the quantity to the third power, is 8r to the third. And you take the volume of the atoms divided by the volume of the cell, and you notice you've got r to the third on the top and the bottom, so you can cancel that out. And you end up with 4/3 pi over 8. Pi is just a number. You can get it from your calculator, and then multiply it by 4 and divide it by 3. And then you take that and divide by 8. This ends up being 4.189 divided by 8. And that is 52.4%. So actually, it doesn't matter what element you're talking about. It doesn't matter how big the spheres are. If it's a simple cubic unit cell, then the packing efficiency is 52%. Because as I just showed, whatever the radius is, it's going to cancel out. So it doesn't matter. And it's always 52%. Okay, another type of unit cell based on the cubic model is the body-centered cubic unit cell. Sometimes abbreviated as BCC. Okay, this is similar to the simple cubic. But there is a whole atom at the center of the cube. Yeah, there's a whole atom within the cube this time, plus the ones at the corner. And because there's an atom at the center of the cube, the atoms at the corners don't touch each other. But they do touch the atom in the center. And that means that it makes it a little bit harder to figure out what the edge length of the cube is in terms of the radius of each atom or sphere that makes it up, because before the atoms were actually touching along the edge length and it was just 2 radii. But this time they're not touching, but they do touch along the body diagonal. The body diagonal is the diagonal that goes directly from one corner of the cube right through the center of the cube across to the opposite corner. That's known as the body diagonal. And so that means you have a continuous line from one corner through the body center, through the center of the cube to the opposite corner. All right, so if we look at an example of a body-centered cubic unit cell, there's one right there. And you'll notice that even though the atoms are in different colors here, colors that kind of remind me of a peanut butter and jelly sandwich, which is making me hungry. Anyway, these atoms normally would all be of the same element. They're just using different colors to make it easier to envision where the atoms are relative to each other. There are some different ways of representing body-centered cubic up here. This right here is more than one body-centered cubic unit cell mounted next to each other. Actually, it looks like it's, what is it? 8? Yeah, it's 8 body-centered cubic unit cells, 4 in the front and 4 behind, so that this one atom at the very center of everything is actually in all 8 of those unit cells. This is the unit cell showing the full atoms around it, beyond what's within the unit cell. And this one here shows what's inside the unit cell. And so this is a little bigger here, so I'll use this. You notice that this atom here at the corner is touching the atom in the center, and that in turn is touching the atom at the opposite corner. So you actually have a through line where atoms touch each other going from this corner here to that corner there, right through the center of the body of the cube. And that is what they end up having to use in order to find out what the edge length is in terms of the radius of one of the spheres. I mean, you can see from looking along the edge of the cube here, there's a radius, but there's a gap in between. So we can tell that the edge length of the cube is going to be a little bit more than 2r, but we don't know how much more unless we actually go through the geometry to find out. And what they have to do is take the body diagonal, which we know is 4r, and from that we can find out the 2 sides of the right triangle that of which that body diagonal is the hypotenuse, and one of the legs of that triangle is the face diagonal. From the face diagonal you can find the edge lengths. And finally, I'm not going to make you go through all of that. Finally, we find that the edge length is 4r over the square root of 3, which actually turns out to be a little bit more than 2r. What is it? 4 over the square root of 3 is 4 divided by 3 raised to the 0.5 is 2.3. So the edge length is about 2.3 r, but in exact terms, it would be 4 over the square root of 3 times r. Okay, I'm gonna actually, we're over 30 minutes, so I'm gonna cut there, and in the next lecture, we'll pick up where we left off.